This is part 2 of the lectures on the kinematics definitions. Towards the end of part 1 of the lecture, I went through the description of average velocity and average speed. That then led us to a description of instantaneous velocity. Instantaneous velocity is the derivative of position with respect to time. In addition to position changing, however, velocity can change as well. That then leads us to what is called acceleration. First of all, let me describe the average quantity, and then after that, the instantaneous quantity. Okay, average acceleration, first of all, is denoted with the letter A. There's a bar symbol above. Once again, this means average, and by definition, average acceleration is change in velocity with respect to time. Okay, now there is a little bit of notation here in the numerator of the expression, specifically change in velocity. Change in velocity delta V is equal to the final value, simply referred to as V, minus the initial value, which is V naught. There is once again a little bit of tail to tip method of vector addition that is occurring here. In order to see the tail to tip method, and you'll see this in an example in just a few moments, we then do the following. Take the initial value and move it to the other side, such that the initial plus the change is equal to the final. Now, because change in velocity, delta V in the numerator of this expression is a vector quantity, this then means that average acceleration is also a vector quantity. Okay, now immediately let's take a look at an example before I then go further and describe the instantaneous quantity. Copy down the next of the lecture examples into your notes. I'll read it to you as well. Okay, a bicyclist is moving at positive 5 meters per second. The plus sign means that the bicyclist is moving by definition to the right-hand side with a speed at that instant of 5 meters per second. 30 seconds later, the bicyclist is moving at negative 10 meters per second. Once again, the speed is 10 meters per second in this case, but the negative sign means that the bicyclist is moving to the left. What is the bicyclist's average acceleration? All right, so we're given a couple of things here. First of all, we're given the initial velocity V naught as positive 5 meters per second, and the final velocity V as negative 10 meters per second. Immediately, we calculate the change in velocity delta V. So the change in velocity delta V is the final value minus the initial value. Negative 10 minus 5 is negative 15 meters per second. And then on a number line representing velocity, here's then how we describe the tail to tip method of vector addition. All right, so this number line here doesn't represent position, it represents velocity in terms of meters per second. So let's say 5, 10 to the right, and then 5, 10 to the left, like so. And now using the tail to tip method, we begin by drawing the initial velocity V naught, that's positive 5 meters per second. That looks like this. And then we add to that delta V, the change in velocity. That's this negative 15 meters per second, like so. So notice I'm taking the tail here of delta V and placing it at the tip of V naught. And I'm, of course, drawing it below the number line such that we can see it. And then, therefore, the final velocity V, the resultant of negative 10 meters per second, that's drawn on the number line in the following way. From the origin, and then 10 meters per second to the left-hand side. So you then pantomime the tail to tip method in this manner in this problem. We have here V naught plus delta V. That then gives us the final velocity V. And now over the time interval of 30 seconds, let's then go ahead and calculate the average acceleration. So the average acceleration, A bar, is change in velocity divided by change in time. So it's negative 15 meters per second, and then divided by the change in time here of 30 seconds. Okay, 15 divided by 30 is just equal to a half. So this is ending up to be equal to negative 0.5. And then here's how the units work. We have meters per second being divided by seconds. Do the seconds cancel out? No, they multiply together to give us then meters per second squared. Here's how you can see how the units work. Think of it in the following way. We're taking meters per second here in the numerator, and then we're dividing it by seconds. That's the same thing, however, as multiplying by 1 over seconds. So then therefore the seconds do not cancel out. Instead they multiply together, and we write the units here as meters per second squared. Average acceleration is a vector. However, I can't draw this vector on this number line because this number line here represents velocity. Therefore, what this means is that acceleration has its own number line. So here's the number line for acceleration, now in terms of meters per second squared, and then right here we'll say it's 0.5 to the left-hand side. So for this problem, the average acceleration vector then, a bar, looks like this. Like so. By the way, at this point, drawing all of these number lines for all of these different vectors is considered somewhat redundant. So because that's redundant from this point forwards, I'm not going to bother to draw the number lines themselves. Just drawing the vectors around in space is good enough. Okay, now this problem here is once again easy to calculate because all that we're doing here is a little bit of basic algebraic manipulation, but it doesn't tell us all that much. It doesn't tell us, for example, what is happening to the bicyclist at some instant in time. All that we know is what is happening at the beginning of the time interval and at the end of the time interval. So average acceleration is easy to calculate, but it's not a complete description of the motion. How do we end up with a complete description of the motion? That's instantaneous acceleration, and it's another derivative. Here's how it works. Okay, let me erase. Okay, so let's say that as an object is moving around in space, what we do here in this case is we plot the following graph. It's velocity as a function of time. And then let's say that the velocity as a function of time is just, once again, some sort of generic smooth curve polynomial, say like so. And then we take a look at two moments in time. Right here we'll say is where we start our clock, and then therefore on the vertical axis the object has an initial velocity v0. Let's say that right here is where we stop our clock. Therefore, on the vertical axis, we then have a final velocity, v. Once again, I'm going to connect the 2 points here with a chord or a secant line. I'll do so by using my ruler. Like so. This point here. And this point here. And now I'm going to go ahead and calculate the slope of that line. Before I do, however, let's denote here that along the time axis, this is once again our time interval, delta t. Okay, now slope is rise over run. Okay, first of all, the rise. The rise, you'll notice, is the difference between these two values, the final velocity and the initial velocity. So then therefore the rise is the change in velocity, delta v. The run then therefore is the time interval delta t. So rise over run is change in velocity with respect to time. This is obviously the average acceleration. The average acceleration, however, only tells us what is happening over this broad time interval. So then therefore, let's say that we're interested in the following. We want to know exactly how the velocity in red is changing at this instant in time. What I then have to do is calculate once again the slope of a line, but we take a limit by making the time interval once again infinitesimally small. That then gives us the following graph. Okay, so now once again, velocity is a function of time. Here's my smooth curve red polynomial like from above. And now let's say that we're taking a look at this specific moment in time right here, this instant in time. In order to calculate exactly how the red polynomial is changing at that instant, I once again have to find the slope of a line. But in this case, it's the slope of a line that is tangent to the curve locally at that point. That then looks like this. So this green tangent line right here only intersects the red polynomial right there at that point. The slope of that green tangent line tells us exactly how the velocity is changing at that instant. This is then giving us what is called instantaneous acceleration. So instantaneous acceleration is now written just as A. It's the same thing as the quantity above, but now we take a limit as the time interval shrinks down to 0 size. It's infinitesimally small. So we take a limit as delta t approaches 0 of change in velocity with respect to time. Once again, in physics AB, you'll see this qualitative description of a derivative written in the following way. However, in honors physics AB and in AP physics C, we use the following notation. Instantaneous acceleration is the derivative of velocity with respect to time. So once again, differential calculus is necessary to describe motion, specifically what is happening in an instant in time for something seemingly as trivial as the following. So what we do here now, as I begin to conclude part 2 of this lecture on the kinematics definitions, is just summarize what I have done thus far. Here is a nice succinct summary. Okay, we first of all have average speed as distance divided by time. Average velocity as change in position with respect to time. That then, however, leads us to what is important, instantaneous velocity. Instantaneous velocity, limit as time approaches 0 of change in position with respect to time, is our first derivative. It's the derivative of position with respect to time. And then we have acceleration. The average value first, which is change in velocity with respect to time. And now we take the time interval and make it infinitesimally small to arrive at instantaneous acceleration. Instantaneous acceleration is the limit as time approaches 0 of change in velocity with respect to time. This is our second derivative. Acceleration is the derivative of velocity with respect to time. All that I have done here in these 2 lectures on the kinematics definitions is I've defined things, and that's it. Position, velocity, and acceleration. Velocity is describing how position changes with respect to time. That's our first derivative. Acceleration is describing how velocity changes with respect to time. That's our second derivative. At this point going forwards, now we start to use these definitions. The more that you use these definitions, the more you understand exactly what it is that they are saying. That will begin in the next series of lectures.